It's fine?
Yes, sir.
Yeah. Okay. Now see. Then again what we have to do is that we have to substitute y x square equal to y. So dx will be just like the last time, dy by 2y to the power minus, and substitute it over here. These two we can cancel out. 4h bar square b square by m, 0 to infinity. Achha, this time we'll get a half coming from this dx. Other than that, if this x square will reduce to y, and then we'll have another piece of y to the power minus half. That means we'll get y to the power plus half this time, right? Y to the power plus half minus 2by dy. Now we remember the formula that tells us 4h bar square b square by 2m. This time n should be 3 by 2, gamma 3 by 2 by 2b 3 by 2. So then finally we obtain the expectation value of quadratic energy, 4h bar square b square by 2m. Gamma 3 by 2 is half gamma half, okay? Root pi by 2. Gamma 3 by 2 is half gamma half. Gamma half is root pi, as I already told you, so that means it will be root pi by 2. So then we'll have, here we have 2b to the power 3 by 2. Now let's calculate. There is a 2 here, there is a 2 here, there is a 4 there, so this will cancel out. I hope I am taking all the factors. Okay, now we have b square h bar square by m root pi by 2 to the power 3 by 2 means 2 root 2. B to the power 3 by 2. That means what? We'll have an h bar square and we'll have an a. Other than that, this will give me a root b. So square root of pi b by 2. So this is the expectation value of the kinetic energy. B h bar square by 2m root pi by 2. Let's see if I've got it right. B h bar square by 2m so I have got correct, but there shouldn't be any root pi by 2x. This is so correct now. We got 2bx, 2bx, and then x square. So we get x square. Then so we'll have a root pi. Okay. Anyway, let's move on. So h bars, b h bars, whatever we have got, b h bar square by 2m into square root of pi by 2. square root of pi by 2. Okay. So this is the expected kinetic energy. Now potential energy. Potential energy is, we know how much is mod a square. So mod a square is 2b by pi to the power half. Then integration half m omega square x square. Then we have to have mod psi square, that was e to the power minus how much? 2b x square.
2b by pi to the power 1 by 4.
2b by pi to the power 1 by 4. Yes, 1 by 4, but then this is basically psi, v psi, right? So there are two pieces of psi, no? One is coming from psi star and another is coming from psi. And each of the psi is carrying a 2b by pi to the power 1 by 4, 1/4. So that makes it 2b by pi to the power 1/2. Is that correct?
Okay, sir. Okay, yes, sir.
But I think I made a mistake in the last calculation. This, maybe I did not take care of this 2 by pi to the power 1. Anyway, let's see how much we got here. 2b by pi to the power half, and then we have half m omega square. Then integration x square into the power minus 2b x square dx. Okay. Again, we'll do the same thing. Y equal to x square. This will become 2b by pi. I think last time I missed this 2 by pi to the power half. So that's why I'm getting an additional. So yeah. Half m omega square. This will then become, first we'll convert it from 0 to infinity. So I'll get a piece of 2 here then. Then we get y here. This will become e to the power minus 2by. And then we know dx will become dy by 2 root y. This 2 cancel out. It will be y to the power half, actually 2b by pi to the power half m omega square, 0 to infinity, y to the power half e to the power minus 2by. So again we'll use that formula. Okay, it's fine.
Yes, sir.
Is it okay up to this?
Yes, sir.
I think in kinetic energy I made a mistake, but we'll correct it. Doesn't matter. 2b by pi to the power half. Then we have half m omega square. Then here we can again use this formula gamma 3 by 2. Gamma 3 by 2 half gamma by root pi by 2. Down below we'll have 2b to the power 3 by 2. This 2 by pi, root 2 by pi will cancel with this. Here is root pi, so we can cancel out immediately. Then you can see there is a root 2 over there, and this is 2 to the power 2 into 2 to the power 3 by 2. Okay, so it's become root 2 by 2 into 2 to the power 3 by 2. That takes care of the factors of. Then we have b to the power half numerator, b to the power 3 by 2 denominator. That means a b denominator, right? M omega square by b. In other words, we'll get this becomes 2 root 2, root 2 to cancel out 4. M omega square by 4. Let's see if that's correct. I degree. Again, I have missed up half factor or root by half m omega square x square. So the half m omega square, and then a piece of 2 comes from here. Is root y, 2 to cancel out.
सर जी शेड्यूल ही करो
Sir,
Yes, bolo.
For at that second last step, sir, you have not written that root pi by 2. You have cancelled that, and you have not written that by 2, sir.
Yeah, thank you. Yeah, that is the mistake I made. Yeah, that's why I'm looking for the 2. Yes, then it will become 18. Yeah, these 2 I missed actually. Okay, that means V is m omega square by 8. And what happens the kinetic energy? Just can I do it? Just one. I will do it very fast. Wait a minute. T. This is equal to mod a square. Mod a square is 2b by pi to the power half. Then the equation e to the power minus 2bx square. So if I take e to the minus bx square, that means minus 2bx minus 2bx whole square. So there is an h bar square by 2m also. Then e to the power minus 2bx square dx. I'm just trying to find out where did I make a mistake. Now let's see. 2b by pi to the power half h bar square by 2m. Here we get a 4b square. Then we have x square e to the power minus 2bx square dx. Same as this one. X square to the power minus 2bx square dx. And we have seen how much we got it from here. 1 to the minus 2by root pi by 2 by 2b to the power 3 by 2. H bar square by 2m, 4b square, and this is root pi by 2 by 2b to the power 3 by 2, same. 2 by 2 by 2b to the power 3 by 2. We got an additional 2 here, that 2 gets cancelled out, so that's the expression. Now we can cancel this to 2 pi, let's see. Let's go 2, okay, so we'll have h bar square. H bar square by m. Then if we consider b, as a root pi we can cancel out immediately. Then consider b to the power half b square, here b to the power 3 by 2. That means this b to the power 5 by 2, this b to the power 3 by 2, that means we get b. Is that correct? 2. The 2 to the power half, the 4 into 2 to the power half, that we are getting from numerator. Denominator will get 2 to 4 into 2 to the power 3 by 2. I think that's it, no? That gives me b h bar square or h bar square b by 2m. Is it correct? Yeah. Last time I made a mistake. I think I made this mistake. So then we got everything correct. T equal to h bar square by h bar square b by 2m. And v is how much? M omega square by 8b. And so then we got the total energy, that is the expectation value of the Hamiltonian, h bar square b by 2m plus m omega square by 8. Is it clear, this calculation?
Yes, sir.
Okay, so now the variation principle comes in. So it says that you can vary your parameter whichever way you want. The minimum value of this energy will be আচ্ছা আচ্ছা ঠিক আছে আপনি চলে আসুন ক্লাস শেষ হয়ে যাবে Okay, so now we'll do the next. So So now the variation. So far we have done just simple calculations of finding out the expectation value, etc., etc. Now the variation principle comes in. So now we can make use of this variation. It says what? It says that H equal to, so far we have got, that is T plus V, that is H bar square by B by 2m plus M omega square by E. B is a parameter. Okay, so trial wave function that we have chosen, okay, it's not a solution of some time independent Schrodinger equation or anything. Okay, we don't know whether it has any relation to that. Okay, we wrote it down out of our sleeve. There is no principle, no justification, no argument. We have, it's completely arbitrary. But this variational principle says that doesn't matter. Now you try to tune your B and try to reduce this energy. You cannot reduce it down from to the ground state, actual ground state energy. Okay. So then what we'll do is that we'll try to reduce this as much as possible, and whatever the minimum value that we got, we could say that that is a close approximation to the ground state energy of our. Is it clear?
Yes, sir.
Yes, sir.
What is the parameter? The parameter is B only. Okay, so let's see. We take the derivative, del B, H bar square by 2m minus M omega square by 8b square, right? And we'll set it to be equal to 0. And from here you can immediately see that if I take the derivative further one more time, del 2h del b square, the first term will go away. The second term would have been 2m omega square by 8b cube, and so immediately we know this is positive. So long as b is positive, this is positive. That means if I set this is equal to 0, that's the minimum for this h. Okay. So then if we set this is equal to 0, then immediately we can calculate b square. B square will be how much? 8 by m omega square, h bar square by 2m. That means what? 4 h bar square by m square omega square. Okay. So in other words, it says B is 2h bar by m omega. If that is so, then we can substitute in and try to find out what is the value, minimum value of this h. So h, then we can evaluate it as h bar square by 2m into this one. Bolo?
I think we need to reverse that, sir. B square is equals to m omega square by 8. That is.
Bolo?
You have written B square is equals to 8 by m omega square. No, sir, but
Wrong, no?
B square is equals to m omega square by 8.
Exactly. Thank you. Yes. It should be m omega square by 8. Sorry. Yes. How much it will be m omega square by 8, no? Yes.
Yes.
M omega square by 8 into h bar square by 2m. And then mm cancel out, h bar square omega square by 16. 16. Is that correct? That means h bar omega by 4. That is the value of b. Now if we substitute it over there, is that correct?
Sir, h square by 2m will be 2m by h bar square.
Yes, sir.
So many mistakes. It should be 2m by h bar square, no?
Yes, sir.
Okay. Look at it. So b square is m omega square by 8 into 2m by h bar square. Now it's correct, right? That means it would be m square omega square by 4 h bar square. Is it correct now?
Yes, sir.
It's correct, right? I hope I have not made it further mistake. That means B equal to m omega by 2 h bar. Very good. Okay, now we'll put it here. H bar square by 2m m omega by 2 h bar plus m omega square by 8 1 by b, that will be 2 h bar by m, right? 2 h bar by m is correct, right? And so the first one mm will cancel out, we'll get 1/4 h bar omega. From the second term mm will cancel out, one piece of omega will also cancel out, we'll get 1/4 h bar omega, so we'll get half h bar. Now you see, we have not solved the Hamiltonian, the time independent Schrodinger equation or anything, but just by using some arbitrary trial function, it reproduces the exact value, the exact ground state interval. That is the beauty of the variation. Without knowing anything, without doing anything, just with an arbitrary trial function, it produces the exact value. Right? Of course, you might choose a different wave functions. Doesn't matter. Only thing is that these wave functions has to have this standard features of the wave function such that it should not blow up, etc., etc. It should be normalizable function. Any normalizable function you choose, it will give the. I cannot ensure that it will give the exact value of free time, but it will give the value very close to the exact value. And if we if we consider this b equal to m omega by 2 h bar, and then we also know that our psi x was what?
E to the power minus bx.
Our a is 2b by pi to the power
2b by pi to the power 1 by 4.
so much problem. What tarika? To be pi by pi to the power 1, and b is we got how much? M omega by 2 h bar. So that means 2b is m omega by h bar. So basically then it's m omega by pi h bar to the power 1/4 e to the power minus bx square. B is m omega by m omega x square by. Now the trial wave function that we have chosen, okay, is very similar to actually the ground state wave function. So that one has to admit. It's not that we have used a completely wild wave function and got the exact value. It's not like that. So we try to we have already in a way undermined the power of the variation principle, and we choose a trial wave function which is pretty much similar to this. That is true, but at the same time, this is very natural to choose a Gaussian wave function. Okay, so it is very natural. Now it so happens that is the exact wave functions in the case of harmonic oscillator, but in general it's not. It is very natural to choose a Gaussian wave function, which falls off as we go from 2 minus infinity to plus. That is actually we have chosen. You can try to choose some other. Okay, and then see what is the value that one. Anyway, is this fine? Any question?
Fine, sir.
Fine, okay. Achha, do you have a class at 12:30 or something? Otherwise, we can discuss one more example and then close it. Is that fine?
Sir.
Okay.
Okay.
Is it fine to everybody? No, there is no further class, right? At 12:30.
Sir.
Yeah.
Yes,
Okay.
sir.
So that we can complete at least this part of the variation principle by today. Okay. The next one again we'll discuss is something which we already know, the exact value, but this time we'll estimate ground state energy of the one-dimensional you can say it's one-dimensional box or infinite square wave potential, whichever you call it. They are actually both same. We know how it is, right? It's like Vx equal to 0 for what? 0 less x less a and infinity otherwise. That means x less than 0 or x greater than 0. That's how it looks like. This is the infinite square. Here only v is 0, here v is infinity. Right? Now we try to find out the ground state. So what is the Hamiltonian again? Hamiltonian is as usual dx square plus vx. Okay, and we need trial wave function. Now this time when we know what are the eigenfunctions. The wave functions, the energy eigenfunctions are sine n pi x by a, but we are not using that. We are using a really peculiar kind of trial wave function, and let's see what we get from that. We'll consider triangular wave function. The trial wave function we are using a triangular wave function. Triangular wave function. Okay, this triangular function looks is given by this ix equal to ax if x is between 0 to a by 2, it's a into a minus x. If x is between a by 2 to a and 0 otherwise. If I plot it, how does it look like? There, you can see how it would look like. From 0, it will rise to a by 2. And then at a, it will come to 0 at a by 2. Like this. It's like a triangle. Okay, and you can see like it's so different from the sine n pi x by a. Sine pi x by a, let's say. Which is actually, the actual ground state wave functions is this. Right? But in a way, you might think that, okay, it looks like it's a kind of approximation, like this nice, smooth sinusoidal, instead of choosing this nice, smooth sinusoidal wave function, we are choosing a triangular wave function, which has like a kink kind of thing. So let's see, like how good it is if we use this additional principle. The first thing we have to do is that we have to normalize it. So to normalizing it, we put 1 equal to, again, mod a square. And then we'll have to integrate in two different ranges. One is 0 to a by 2. There we have it x square dx. And then a by 2 to a. There we have to integrate it a minus x whole square dx. But these are algebraic terms, so it's very easy to do this integral. Mod a square we get from here how much? X cube by a 3, x cube by 3, 0 to a by 2, plus how much is this one? If I put y equal to a minus x, then it becomes 0, a by 2, minus, actually same. If we put a minus x equal to y here, then you can see this integral is same as this integral. This integral is same as this integral. Basically, you can put a 2 over there, sufficient. So that means it is a cube by 8 mod a square a cube by 12 equal to 1. In other words, a is 2 root 3 by a to the power 3 by 2. Is this fine? You have to, so this part I didn't do. Yes. This part I didn't do. You have to do this substitution. So y equal to a minus x. And if you do this substitution in this integral, you will see this integral will again reduce to the same like x cube by 3 from 0 to a by 2. And so that's why I put a piece of 2 over here. Is it clear? Yes. Is it fine with everybody? If not, let me know, then we can do it explicitly. Shall I do it explicitly or not required? Sania? Internet problem. No? Is it fine?
Yes, sir.
Yes, sir.
Yeah, okay. Okay, shall we go ahead?
Yes, sir.
Okay, so then this is the value of that we obtain from the normalization. 2 root 3. Let me see if I have got it correct. There goes 2 root 3 by a root a. Root 3 by 8. Okay, so the normalization part is done. Our next task is to find out the expectation value. Hello, just one moment. হ্যাঁ হ্যাঁ বলুন আচ্ছা আচ্ছা ঠিক আছে from 30 a equal to 2 root 3 by a root a. And so our next task is to calculate the expectation value of I. Okay, so let's do it in another. Now here actually we have to be a little let's see. Once again we know that there is a t. T is what? T is integration I star minus 8 bar square by 2m d square dx square psi. Okay. This psi is given here. And then immediately we know that these integrations, first thing is that these integrations will be limited only to 0 to a, because beyond that psi will vanish. Second thing is that we can always make a by parts and bring one of these ddx on the psi, and this psi, as you can see here, it's real. So psi, and we will not distinguish between psi and psi star, and so then we have got the psi dx. this is what we have to. How much is d psi dx? From here we can immediately read d psi dx. So d psi dx will be a for 0 less x less a by 2, then minus a by 2 less x less a, 0 otherwise. Now if we want, we record this. Wait a minute. Let's see if we record this. Step function, etc. Okay, so here we didn't do this. Is it required? Let's try not to use it. How much we'll get if we don't use it? It's not required actually. Okay, see here I have done in quite elaborate. May not be required. So t, let's do it fast then. D psi dx is plus a or minus a. D psi dx whole square is a square always, right? And since we have done in by parts, this sign has changed. So we got h square by 2m, and d psi dx square, you can see it's always a square. So I put a square there, and then it's an integration from 0 to a. So I'll get a piece of a. Is it clear?
Yes,
Is
sir.
it clear? Is it clear? Otherwise, if not, please let me know. I will do it more explicitly. Badruj, is it clear? Not around. Sanchita?
Yes, sir.
It's clear, right? Is it clear, or should I do it explicitly?
Do it.
Do it, okay. Very good. Yeah, at least if you tell me, then I get a clear idea. Okay. Anyway, so we are calculating this. So expectation value of h bar square by 2m. This integration, range of integration 0 to a, will split it. We'll split it into two different parts. Actually, more than two. Two different parts. 0 to a by 2 and a by 2 to a. So first we'll put 0 to a by 2. 0 to a by 2, then d psi dx whole square dx plus a by 2 to a d psi dx square dx. And of course, beyond that, psi is 0, d psi dx is 0, so there is no point considering the contributions will come to be equal to c. Now we're left with h bar square by 2m. How much you get from d psi dx square? If you look at this range 0 to a by 2, 0 to a by 2, you can see the value of d psi dx is a. So it's constant. So we square it, we'll get a square over here, and then it will become 0 to a by 2 dx. Similarly, when we come to this place, this a by 2x to a, we see the value is actually minus. To square it, we'll get again plus a square, and then once we get plus a square, we know this is a constant, so we can pull it out, and then we are left with a simple integration. Let's do this integral. H bar square by 2m, a square, let's write it outside, and then you can see here in this integration, so we get a by 2, here also, no, it's fine, a by 2 to a, so this is the upper limit, this is lower limit. This also a by 2, and we will be left with h bar square by 2m, s square, and not a by a. Is that correct? Is it fine?
Yes, sir.
Yes.
Okay. So we got like h bar square A by 2m. And how much is a square? We know a square. A square is, we have already calculated. A square is from here. A square is how much? 12 by a cube. 12 by a cube. So we substituted that. 12 by a cube. That means we get 6 h bar square by m square.
So one more A is there
Ruko, one more is there.
in the numerator.
H bar square, then this A is there. This A is there. I have written it here. Then this capital A square give me 12 by a cube, so it is a cube. A and a cube, so I cancel one A will cancel out, I'll get a square. Is that correct?
Yes, sir.
Yes, sir.
This much is not required. Okay, I wanted to did it very. Yeah, so this is the one. And now you can see what is the exact ground state energy. The exact ground state energy is pi square h bar square by 2m square. Okay, so we got 6h square, 6h bar square by m square. So we got 6h bar square by m square, and the actual ground state energy of infinite spiral potential is pi square h bar square by 2m square. Okay, and if we plug in the numerics, I have not done it here. Anyway, I can do it. How much is pi square by? A minute. Just one moment. Four point 9348. H bar square by m. And this one is then 6 h bar square. Because this is the error because of the approximation that we have. Instead of 4.93, we are getting 6. But you can see there are two things to see. First thing is that it's very close. 6 is not so different from 4.9. Second thing is that it has reproduced all the parameters appropriately. Of course, you might say that it will always do it because of dimensional analysis. That is kind of correct. Of course, third thing, if you consider our wave function, it was extremely crude. It was extremely crude, and we didn't even keep any tunable parameter here. Nevertheless, it reproduced almost the exact. So here is our function. Extremely crude, as you can see. So as I said, like this is the ground state wave function. It's a nice round shaped smooth, and we have approximated it with a triangle. But still it gives quite nice. Is it fine?
Yes, sir.
Any question? Any question?
No, sir.
Okay. Okay, then we'll stop here. So in the next class, we'll discuss the helium atom, where again one can use this variation principle to obtain the value of the energy. if time permits, we'll discuss a few more problems because the variation principle is kind of interesting and it also appears in various contexts. But let's see.